So we'd like to look at another hypothesis test. So here we have a situation. It says the following. Last year, university students worked an average of 19 hours per week. 19 hours per week. That was last year. This year, a random sample of 28 university students is selected, and their average time spent working weekly is 20.1 hours, with standard deviation 2.4 hours. Use the 1% significance level, that's 1%, right, 0.01 significance level, to test the claim that students this year are working the same amount of time as last year. Okay, so we're trying to test the claim students this year working the same amount of time as last year. So we need to, if we're doing a hypothesis test, step one. Step one, we're going to state the null and alternative hypothesis. So that's going to be an H0 for null, right? And an H1 for alternative. And these are always going to be about population means, mu. And remember, the null always involves the equal sign, right? Null always involves equal sign. So what are we trying to test? We're trying to test the claim that this year's students are working the same amount as last year. Students this year are working the same amount. So the average of this year is the same as last year. What was last year's average? 19, right? 19. So this is actually the claim we're trying to test, right? The average, the mu this year is the same as last year. So mu is equal to 19. 19 was last year's average. So if the null hypothesis is the claim we're trying to test, then the alternative would be that the mean is not 19, right? The mean is not 19. Okay, so step one is done. So step two, we want to consider finding critical values. Find critical values. So first of all, we want to think about what are we going to use? Are we going to use a t-distribution or a z-distribution? Well, if you look at that standard deviation of 2.4 hours, that standard deviation of 2.4 hours, that's referring to the sample of what? 28 university students. So that is an S, right? 2.4 hours, that's an S. So the sigma is not known. Population standard deviation is not known. So when you have the sample standard deviation only and not the population standard deviation, we're going to use t-distribution, right? T-distribution. Okay, so also how many tails? Left tail, right tail, or two tail? Well, we know we're going to use two tails because when you look at the alternative here, the alternative hypothesis involves a not equal to. Anytime you have a not equal to for your alternative, you're going to have to check potentially the left or right tail. So you have to look for two tails. So to find the critical values, let's draw a picture. Our t-distribution. Zero's in the center. You're going to have two tails. And in this two tails, you're going to have your significance level, right? The left tail and the right tail. So that's the probability of rejecting the null hypothesis when it's actually true. So that's the area and two tails. So that's called alpha, right? 0.01. 0.01. That's what we were asked to test at, right? The 1% significance level. Let's read. Use the 1% significance level to test. Okay, so the two tails, the area and two tails. Area, two tails is 0.01. So our goal here is to find a T lower star and a T upper star that separates the rejection regions from the non-rejection regions. So when you have an area and two tails of 0.01 and you have degrees of freedom, what are degrees of freedom here going to be? Degrees of freedom, well, you're going to take your sample size, which if you look closely, it was, what, 28 university students? It's 28 minus 1. So you take the sample size minus 1, and you get degrees of freedom are 27. So I'm going to look up degrees of freedom are 27. The area and two tails is 0.01 to get my T upper star. And then from that I can find my T lower star will just be the negative variation of that. So let's look up area and two tails is 1% and degrees of freedom 27. Let's do that real quick. So here's my T table. So I have area and two tails is what? 0.01. And degrees of freedom here, 27. So when we match the area and two tails is 0.01 with degrees of freedom being 27, we find this number here, right? 2.771. 2.771. So that's our T upper star. So our T lower star, that's going to be on the other side, that's going to be negative 2.771. That's going to be the negative. So we have these two critical values. Okay, so finding the critical values is done. Step 3. We're going to compute the test statistic value. So we know we're dealing with T's, and the formula is going to be what? X bar minus mu divided by S over square root of n. And here n is going to be the sample size. It was what? 28 students were randomly selected. X bar, remember, was 20.1 hours. That was the average that those 28 students worked for every week. Where was that? Right, 20 hours. A random sample of 28 university students is selected, and their average time spent working weekly is 20.1 hours. Standard deviation is 2.4, right? So S is the sample standard deviation for those students was 2.4. And for the sake of argument, we're going to assume that the population mean is equal to, we go back to the null hypothesis, 19. Right? 19. So we plug these numbers in and calculate the T test statistic value. It's going to be 20.1 minus 19 divided by 2.4 over square root of 28. So you calculate this, 20.1 minus 19 is going to be 1.1, and divide this by 2.4 over the square root of 28. Make sure you put parentheses around your bottom there, and when you calculate this, you should get the following. T is going to be, let me see here, I got T is 2 point, and you want to take it to 3 decimal places, 425. Okay, so step 3 is done. We have the test statistic value. So step 4. Make a decision about the null hypothesis. H0 is the null hypothesis, right? If you go back and draw a picture of your t-distribution, 0's in the center. You have these two tails here. These make the rejection region. So here on the left, remember you had t lower star, and on the right you had t upper star. What was t lower star? Let's see. Negative 2.771, and t upper star was positive 2.71. So this is negative 2.771, and this is positive 2.771. So these numbers separate the purple rejection regions from the non-rejection regions. And what was our test statistic? We just computed our test statistic. It was 2.425, right? That's the orange number. Let me get an orange number here. So our test statistic for our sample information was 2.425. Where is that? Well, that is somewhere in between 0 and 2.771. So this is in the non-rejection region. So because our test statistic, 2.425, is in the non-rejection region, we're going to fail to reject. Fail to reject. We're not going to reject the null hypothesis. So let's pay attention. We failed to reject the null hypothesis, and the original claim involved equality, right? The original claim was the null hypothesis, so it involved equality, and we failed to reject the null hypothesis. So in step 5, we're going to actually write our, what you call, conclusion, step 5. Summarize conclusion. Now let's look at the wording. We go to our wording sheet. We're going to scroll here. Focus on the wording. Does the original claim, that's the claim we were testing, contain equality? Yes, right? Did we reject the null hypothesis? No, we failed to reject the null hypothesis. So we're going to go here. There is not sufficient evidence to warrant rejection of the claim that, that's what we're going to write. There is not sufficient evidence to warrant rejection of the claim that, and then let's write our claim. Let's remember what our claim was actually. The claim that we were trying to test the claim that students this year are working the same amount as last year. Students this year are working the same amount as last year. There is not sufficient evidence to warrant rejection of the claim that students this year are working the same amount as last year. So what we're saying is, based on our sample information, our randomly collected sample information, we don't have enough evidence to reject this claim that students this year are working the same amount. So we can't reject this claim. So they could be working the same. They could be working the same as last year, the same amount. All right, so there's another hypothesis test. Well, this turned out to be a, well, let me scroll. This turned out to be a two-tailed, right? A two-tailed t-test, right? Two tails. Two-tailed t-test.